Our speaker is Dr. Ceni Babaoglu. We're so happy to have her giving a talk for the SIAM Student Chapter QA series. And we know each other for a long time, I think since 2000. So I'm glad to have her. She's going to talk about from mathematics to data science. And you can take over the stage, Ceni.
Thank you very much, Özkan. I really appreciate this invitation. Thanks for having me. And thank you everyone for attending this session. Yeah, this is kind of an informal talk, so feel free to jump in, ask questions or comments. So I will be happy to have your comments, while we are going on. Or if you like, we can have a question and answer session at the very end as well. So I prepared some slides, so to make it, although it is informal, to make it a little bit like formal. And I will share my journey with you from mathematics to data science. And so, sorry about that. So let's start together. So a little bit about me. Actually, my research in mathematics is really going back to 2000 to 2015. So my research areas were mostly partial differential equations and symmetry problems on overdetermined problems. And, I really gave like 15 years or so to research in math. And it is very interesting that after getting my associate professor position, I passed my research area to data science. So, and of course, while I was doing research in mathematics, you can imagine that I was teaching calculus, linear algebra, differential equations, partial differential equations. And you can imagine my life right there in mathematics. I know that most of the participants here are coming from math background. So you can imagine my life there, right? So, and then in 2015, exactly 2015, I changed my direction to data science and I started to teach courses in data science. And while I was teaching, I was learning as well. And I realized that we are all time learners mainly. So there was a nice saying that if you want to learn better, teach it, right? So that is how I started somehow. And it was, for me, it was very exciting to see how much math we use and is needed in data science. So that is pretty much what I will be sharing with you today. And this data analytics, big data and predictive analytics was a new program in Ryerson University. And we started this program, and the courses that I prepared was teaching, let's say the courses that I was teaching was something like new courses. So I developed the course materials like modules and prepared video lectures for them. And we were having the lab sessions in class, in the computer lab classrooms, but somehow we were doing it in a hybrid fashion. So this means that the students were watching the videos, coming to classroom, and then we were doing the labs. Of course, after pandemic, everything changed, and last winter we put everything to fully online version. So these are the course that I developed, video lectures and lab exercises, and I have been teaching these courses quite for some time. And practical data science and machine learning is our new program. So practical approaches in data science is the new course that I'm teaching this term. Again, I prepared video lectures and lab exercises, and we are having online sessions as well, drop-in live sessions where students can discuss, ask their questions, and we do the lab session together. And I'm teaching 2 courses in the master's program as well. But as you see, all the courses that I'm teaching is mainly in data science. So, and my research is now in data science as well. And today, I will share with you some of my research, but in a way that I will share with you how math is used in these researches, and all the projects that I'm sharing with you today is published in either a conference paper or a journal paper. And those were collaborations that we were having with industry partners as well. So the first one was about predicting modeling of lapse risk. So, and it was about sorry, about, it was on insurance data mainly. So, and the next one was about collisions in Toronto. That was really interesting. And in that research, we mostly focused on the exploratory data analysis, but we did predictions as well. And in this today's session, I will, give some insights about those researchers as well. So the third one was about recommender system for recommendation system for news articles. So it was for Globe and Mail. And the last two that I wanted to share with you is a project, two different projects that we work with St. Mark's Hospital. So you will be seeing this some visualizations from these projects as well. And yeah, I will take it from here. This is a little bit about me. Oh, sorry, the last one is also with St. Mark's Hospital. The last three projects that I mentioned today here are again with St. Mark's Hospital. Okay, so let me say a few things about my outline first. So working in data science, the concept needed, communication across disciplines is the first thing that I want to discuss with you. And then I will take you to how to conduct research in data science. So since the participants here are mostly having a math background, somehow it can be a good roadmap for those who are interested in doing some research or writing papers in data science. So that's why I will be discussing how to structure a research problem or research project in data science, defining the research problem, reviewing the literature, conducting quantitative analysis, and then publishing, if you like, a research paper or your project that you're working on. Providing a reproducible research, especially in data science. Why is it important? Why is it different than the other majors? And I will also discuss the structure of a paper or a project. And maybe later on, we can discuss a little bit about the future of data science as well. So working in data science, so mainly we start with a business problem. So that is a little bit interesting, a little different than the math major, I may say, because somehow at the end of the day, when we are doing research in data science, our target is to turn it into maybe a business decision. Or maybe if we're working on healthcare data, taking it to a level that will be really important for hospitals or for our patients, right? So that is how we are taking really a business problem and translating it into a data science problem. It can be a machine learning problem, it can be a problem that we are doing predictions, or it can be a problem that we are really doing data mining and exploratory data analysis and finalizing the project without doing any prediction at that point. Especially at the stage that when we are using deep learning, that can be the scenario as well. But at the end of the day, again, we are taking a business problem and translating it into a data science problem. Sorry. And of course, when we transfer it into a data science problems, we are starting to apply data science techniques like statistics, machine learning, data analytics are at the back, coding is for sure there. And then we create predictive models. As I mentioned, I mean, it depends on the research problem, but in most of the research problems, we go to prediction, but it can be an area or a research problem that we are not doing prediction, but doing exploratory data analysis and data mining in an advanced fashion. And then, of course, validating the results. So I will mention a few things about there too. So when we finalize the project, mostly there is no happy end for us. If the evaluations are very high, right? So let's say around 98% of prediction. So we will be dealing with the overfitting problem. But if the accuracy is low, that is not a good result either. So at the end of the day, we see data science and predictive analytics a way that it is an iterative process. And mostly there is really no happy end at the end, and there is always room for improvement. So we can put it in this way. So I will say a few things about that as well. And producing meaningful conclusions, inferences. So taking it, since we are taking it from a business problem and transferring into a data science problem, of course, at the end, our suggestions, predictions, and also inferences about the data set will be important. And mainly it is really what the data set is telling us. So concepts needed in data science. So that is really something that I like a lot. So first, some basics. So for example, here, when I say, let's say cosine similarity. So cosine similarity is something that we know from math. And by the way, this math is not in a very advanced level. I wouldn't say that it is in the master's or PhD level. Even undergrad level math is giving us a lot. So giving us a lot of area that we can focus on data science and do understand algorithms and even come up with some new algorithms or generalize algorithms. So that's why, I mean, when I say math background, don't think that it is a very high, level of math. So undergrad level will be perfectly fine. And when I say distance measures, for example, there are algorithms who are using the distance measures. So K nearest neighbor algorithm and K-means clustering algorithms, which is K-means clustering is really a clustering algorithm, the baseline, the first clustering algorithm that you can think immediately when you say clustering. And when you go to K nearest neighbors algorithm, it is both used for classification and regression problems. So, I mean, by default, when you say KNN, I understand classification, but you can mention KNN regression, that, oh, okay, so you can do regression as well. So you're using KNN for regression. But, you know, when you are chatting with people, when you say KNN, it is a classifier mainly. But these algorithms are using distance measures, and they are using similarity measures and distance measures. So remember Euclidean measure, Manhattan, Minkowski. So all of those are even in the packages of R or Python programming languages that you can, play around with the parameters, go to a similarity measure, let's say cosine similarity, or go to a distance measure, choose Manhattan or Euclidean. So, and then of course, statistics, okay? Statistics is there, the distributions, and especially normal distribution, very interesting. I mean, these distributions are taking part, especially in the exploratory data analysis and in the initial analysis. So in terms of the data attributes, you check their distribution. So if it is away from normal distribution, as you know, you need to go to non-parametric statistics. So if it is normally distributed, the groups that you're comparing or the data attributes that you're comparing are away from normal distribution, then you go to non-parametric version, right? So those ANOVA, Kruskal values, or t-test, or Wilcoxon rank sum test, or the non-parametric version of ANOVA, like Kruskal values or Friedman test, let's say, if you have a block design. So all of them are there. So we are using them frequently. And it's not only in the exploratory data analysis, actually, when we are doing predictions, right? So let's say I'm doing KNN and comparing with logistic regression, right? So at the end of the predictions, I'm evaluating them. And this is the first question that I'm asking myself. Okay, KNN is doing better than logistic regression, but is there a statistically significant difference between them? Or they are doing pretty much the same? So this is, altogether the big picture, the scenario that we have in modeling or in exploratory data analysis, that we really need that, hypothesis testing and normal distribution. Interestingly, normal distribution is also used as an assumption for machine learning algorithms. I mean, I may say most of the machine learning algorithms are using normal distribution as an assumption. So that's why, I mean, that those basics from statistics is, of course, in data science. And then calculus is there. So that is really, I like, that is something.
We have a question in the chat box, if you can address that, please. There's a question in the chat box. Richard says, like you said several times, like data mining, data science, machine learning, deep learning, etc. However, he says like he's not sure that many students know the differences between these different topics. What is the difference between data mining and data science? And what is the difference between machine learning and deep learning? I think you can answer that question. That was a long question though, but please answer and go ahead. I'm sorry to interrupt. So
thank you for that, Özkan. And
sorry about the link.
Visualizations as well. So I can mention that with some examples. For sure, I will do that. So thank you for reminding me. So now I can see the chat area as well. And, feel free to, if you like, unmute yourself and ask your questions. I will be more than happy to answer. So that is on me. I will mention the differences as well. So, and I have some slides about, conducting quantitative analysis. So when I'm passing to those slides, so I will mention the differences as well. Thank you for that. And so in terms of, again, concepts needed in data science, so calculus is there, differentiation, approximation, and optimization problems. So that is also something that I want to share with you, because differentiation, again, in the level of undergrad level, differential equations or differentiation, I may say differential calculus as well to that. So not even taking you to the differential equation course mainly. So there are some algorithms that, for example, neural network is working on differentiation. So when we say machine learning, it is mainly just think that you're using algorithms that you're training your algorithm and your model on a data set, on a training set, and then you have a small portion on your pocket as a test set, just to give a simple understanding. I mean, the simple idea behind. So it will not be like a course that I'm discussing with in detail, but still, I can give you the basic idea behind. So you have a training set, let's say you have millions of rows and you have a training set like around 80%, and then you have 20% of that data set, like millions of rows again, and it is in your pocket. So you're running your algorithm on the training set, and then on the test set, you're doing your predictions and you're doing your evaluations. So somehow the algorithm is running on the training set, learning from those examples, and running on the test set, and checking the evaluations there. So in a very simple idea, so this is mainly machine learning. So you're using machine learning algorithms and you're doing predictions and you're training the model, testing the model. So this is mainly with the simplest form I may mention is machine learning. So there is prediction there. So data mining, I will come to that. So here, for example, when I say neural networks, with neural networks, just like k-nearest neighbors, you can do predictions, okay? And while you're working on the training set, the algorithm is doing using differentiation, just like partial differentiation, very simple partial differentiation, and that is called backward propagation. So backward propagation is somehow optimization problem, minimizing the error, going to the training set again and again with minimizing the error. So while it is this much dynamic, it is different a little bit from other algorithms. Neural networks is giving mostly better accuracy and better performance. So actually that backward propagation is working, really. I mean, if you just think about the simple idea behind. And what is using is just partial differentiation, basic partial differentiation. And when you say, for example, support vector machines, so there is an algorithm which is called support vector machines, and it is working on mainly, that is also interesting, again, optimization, but optimization with some constraints. So what would you say to that? Like Lagrange multipliers, right? So you have a minimization problem, but in the meantime, you are running some constraints at the back. So the thing that we have seen in undergrad math as Lagrange multipliers is playing a really important role in support vector machines. And then the idea of hyperplane, the definition of hyperplane, is also used in support vector machines. And linear algebra is there. Linear algebra, so just think that, when you are working in data science, you're working with big, like huge matrices, right? So you have many attributes. The idea is the rows are, the rows in your data set is mainly your instances, your measurements, observations, but the columns are the attributes. So you're working on big matrices. So of course, when you're working with them, dimensionality reduction is becoming an important process because you're working with huge dimensions. How can you, reduce the dimension there? So there you go, eigenvalues, eigenvectors, transformations, diagonalizations. So all of these, simple things that we have seen in math is becoming crucial, important, basic idea again behind of principal component analysis. Linear algebra is always there. I saw the chat area comment. Exactly. Linear algebra is always there. So principal component analysis is mainly working on the on a transformation, let's say. So from a higher dimension, you're reducing your data in terms of like matrices, rows, and columns to a reduced space. So in principal components are used there. And that is really interesting. I mean, when you read a little bit about that, I think you will be impressed as well. So without, without deleting any columns, without deleting any attributes, it is using linear combinations of the attributes and doing some dimensionality reduction. And instead of attributes, you're using principal components. Each principal component is a linear representation, in a linear combination of the attributes. So can you imagine, instead of taking the attributes, you're taking the linear combinations of them. And instead of taking hundreds of attributes, you're reducing it to, let's say, 20 principal components where all the attributes are living in it. So of course, I mean, these are really concepts that we are teaching in our courses, and it is taking time, right? So for example, 1 week I'm working on principal component analysis, right? So 1 week goes to K nearest neighbors algorithm. So this is just giving you the flavor and the intuition somehow. Single valley decomposition is something that is, again, goes to dimensionality reduction. Of course, with tools, there are other tools that I can mention, but these are to do data science, we should know. So I may say that R and Python, those are of course, machine learning algorithms. And then, of course, when you need to go to big data, of course, the environment, Hadoop ecosystem can be helpful as well. And then if you're going to do machine learning on a big data, like real big data, and especially when you're working with images, videos, of course, Spark will be there. Tableau is for visualizations. And I know that visualizations are taking a lot of attention, right? So we like visualizations. So that's why, Tableau is taking attention as well. So you can do your visualizations in R or Python, but if you want to have a little bit more fancier graphs, you can go to Tableau as well. So, you know what, this is something that I want to share with you as an example, because, I really believe that interdisciplinary work and research is becoming more and more important, and data science is exactly that. So in data science, we really know that data science is interdisciplinary. And look at this. So since it is interdisciplinary, of course, the communication and the collaboration skills will be important. And here, maybe before going to that example, I may mention one thing. So for example, normalization, right? We all know normalization, right? But normalization in principal component analysis, for example, is a terminology that is used in data science. And it is mainly, for me, it is centering and scaling, but it is called normalization. On the other hand, let's say you have some numbers, right, between minus, or let's say 0 to whatever million, and you want to put it into a range of 0 to 1. So that is normalization as well, right? So some concepts like normalization, standardization, or in other terminology as well, or other definitions as well. So it is very important to have clear communication, okay? Just like the thing that I said for KNN, right? When you say KNN, for me, it is a classifier. So to mention that it is regressor, I have to say KNN regression algorithm or KNN regressor. So you know what I mean? So in terms of different terminology, so to make the communication, let's say, easy and without any misunderstanding, sometimes we need to talk more, right? So we sometimes need to mention that, oh, you know what? Okay, so I'm using t-test, but I'm using the pair t-test, okay? So, or I'm using normalization, but I'm using this, formula or this approach for normalization. So here is one example. I may say linear algebra versus data science, or linear algebra versus statistics, if you like. So one of them is saying length of a vector, the other is variability of a variable. So angle between two vectors, So just think that data science is taking each vector as a as an attribute feature. So each attribute is a vector. So the vector, the angle between them, if you go to the cosine of that angle, you go to correlation, right? So the other one is angle between two vectors. So, you may say that angle between those two vectors is, close to pi. The other will say that, oh, you know what, they are negatively correlated. So, that is a really good example, very simple, but with the simple example, it's not that I'm teaching, but I'm giving you the intuition about this two different disciplines, right? So how we can collaborate, how we can communicate. Okay, let me go. Okay, sorry, I have a question in the chat area.
Go ahead, there's a question. Yeah. Do you want me to read that?
Yeah, I'm just reading it. So when I say decomposition and PCA and single variable decomposition, I mean dimensionality reduction. So if you want to go a little bit deeper in that, just go to dimensionality reduction. Matrix factorization that I didn't mention here, matrix factorization, single value decomposition, latent discriminant analysis, and then principal component analysis. So these are the main dimensionality reduction techniques. So when I say SVD, yeah, single value decomposition, or PCA, I really mean dimensionality reduction. So now I will take you to the part that, I was discussing research. So how do we start our research? So first of all, we structure our research project. So as I mentioned, in data science, especially the projects that the research that I was doing was all coming from a data set itself, right? So for example, the one that I was mentioning about collisions was open source data set. It was about Toronto Police Services collision data. It was open source. But the one which was coming from St. Mark's, of course, it was healthcare data, and it was not open source, although it was anonymized and the privacy of the patients were, of course, ensured, but still it was not open source. So these are the project that I'm working on are all coming from real world data. And we are structuring the research project. First, the research defining our research problem, and then going to literature. So literature is, again, also just like in math, data science, in data science as well, it is extremely important. And we did a literature review not only for the techniques that has been used in literature, but also for the domain expertise. So to understand the domain, to understand the attributes, to understand the nature of the data. And then, we have to do a really good literature review and then initial analysis, and then we go to any data mining or machine learning technique. And conducting quantitative analysis, is the next part that I want to mention. I think I'm going fine now. Okay, sorry. Özkan, I'm receiving some emails that mentioning that they cannot attend the Zoom meeting. I don't know.
Can you share the one that you just got into? Like, just share that Zoom.
It is coming from LinkedIn. Do you mind tagging me in your post or something?
Let me just, I'm just going to share it in the chat box here. There you go. So this is the Zoom link that we share. And then YouTube link is already shared. Do you want me to do it again?
I already, YouTube.
Let me just share.
I'm not sure.
I shared two links here. You can share both of them if you want to.
Okay, let me reply to this.
Sorry.
Oh, I'm sorry
She shared the link. Dr. Babaoglu shared the link with their with her students and everything in Canada. So, but we got mixed up in another Zoom meeting. I think so.
Okay, sorry about that. Yes, I'm back. So yes, I was checking the time, and then I realized that there was a problem with the link. Perfect. So I'm good with the time, right? So as you know, I talk a lot. Okay, so but I will take you to a good place, okay? So yeah, structuring the research project. So first of all, what are you going to do, right? Really the subject of your research project. So why are you going to do it? The reason. So of course the reason can come from your stakeholders or from the collaborators that you have in industry or in government or in a hospital. So how are you going to do? These are exactly the research methods. So, and when are you going to do it is the plan of the work. So mainly it is, I may say that it's a research project. It's not about data science mainly, but if you're structuring a research project, you have these, right? It is not something special for data science, but still whatever I have here is in terms of data science. So defining the research problem. So this is somehow important for us because the one that is needed in industry or the one that is needed in the let's say by the companies or stakeholders can be a little bit different, right? So something that they have in mind can be a little bit different when we see the data, check the data, understand the data, and start working on the data set and focusing on the research problem. So that's why I wanted to put some bullet points here as well. So especially in deciding the scope of the problem, and then what to expect and how to finalize. So and I have a very interesting situation here. So sometimes we focus so much on the prediction. So as data scientists, and when we are doing some data science, working on data science projects, let's say, prediction is taking really a lot of time for sure, but also we are so excited about the prediction results, right? But what I learned for example, in Toronto Police Services project is that it was not about the predictions. It was about the exploratory data analysis as well. And that is really interesting. The data set that we worked on was all killed or seriously injured data. So what I mean by that is that each row that we were working on, like each row in the data was either describing a person who is killed or seriously injured. So in that project, so the exploratory data analysis was at the end more important for Toronto Police than the predictions. So why? Because we could come up with some suggestions, and they could use those suggestions in their campaigns. So that's why exploratory data analysis, and I have a slide for that as well, is really important. So scope of the problem is important. Of course, there are limitations, but also, how are we going to use this at the end? How are we going to finalize this project? How are we going to know that this project has succeeded? So just think about that, right? It's not really about, everything is not about predictions and accuracy results or precision results or recall results, but it's also about the data set itself, and data mining, exploratory data analysis can, somehow take an important part there. So in terms of literature review, I know that, since you're coming from a, math major, so it is pretty much the same. I would say reliable web sources, because in data science, and especially in this era, even, this meeting is video recorded, right? So everything is more about visualizations, videos. And when you go to some, let's say, when you want to go to some literature where you need to read and learn, so of course you go to videos as well. YouTube will be there, or websites will be there, but go to reliable ones. And especially in data science, when things are interdisciplinary, and we don't have, like textbooks like calculus, right? So just think about that. Just think about your textbook in calculus, how many questions, examples you have, right? So, but in data science, of course, we don't have that yet, but it's coming, for sure it is coming. But in terms of the exercises and learning materials, and when you go to literature, so we have to be, let's say, we have to be a little bit conscious, and also careful that we really go to the correct material, right? So it should be reliable. So that's why personally, instead of web sources, I prefer to go to still conference papers or journal papers or peer-reviewed articles, so that we can have a better understanding who is doing what and how in the literature. And yeah, link across discipline boundaries are of course important in data science as well. And in the meantime, I think thinking about
I have a question. I'm sorry. So does what you were just referring to, that fact, kind of relate to why the master's classes that you're teaching are the topics that they are? I kind of remembered the 2 master classes that it had to do with like research techniques and stuff.
Exactly. One of the courses that I'm teaching is research skills. So in research skills, mainly we are preparing our students for their major research project. It's like a thesis. Major research project is, and getting ready for that. I'm discussing mostly about the experimental design, the steps of the analysis. For example, there the students know what KNN is, what SVM is, what PCA is, or what correlation is, but we are working on the structure of the project, and how to write the project, how to write a paper out of that, and also the experimental designs of the research projects. Yeah, exactly. That is the one that was mentioning as research skills. That is correct. But also we have project course in the big data and practical machine learning programs, and also there our students are writing their project and they are doing a literature review as well. But of course, master's is a little bit in a higher level.
I have a quick question, just because I'm curious. In the courses you teach, is there a significant differentiation made between supervised and unsupervised algorithms, or are they all kind of just taught together?
Oh, there is a difference. So, for example, in the courses, but of course, before going to supervised learning, before going to machine learning, because supervised learning and unsupervised learning all again are machine learning algorithms.
Mm-hmm.
So, if you go to, for example, CIND 1, 2, 3, in my first slide, I had that. So, the first course is mentioning the basic methods like distributions, some visualizations, structure of the data, different data types. And then we are doing a little bit of 1 week for linear regression, 1 week for correlation and understanding and using. Of course, all of them has codings and labs as well. And the advanced methods course, in the advanced methods course, which is the first course was a prerequisite, and then when we pass to the advanced course, then we discuss supervised and unsupervised learning. And yes, we do that separately. So we do clustering. We discuss 1 week for clustering, another week for classification, like which is working on label data. We have to give some time. So when I was mentioning, for example, distance measures, KNN, K-means, so if you want to use Euclidean distance, for example, both of them are using, but the way that they are using is different. So unsupervised and supervised learning are totally different things. Maybe at the end, when we have a little bit more time, I can discuss a little bit more. I mean, since you are curious about that, but for sure in the courses, we are teaching this. It is not something that is coming from math. That is correct. We need that math background. And if you have the math background, you can make things really, really different, like with understanding, right? Because that is a power, I guess. So in data science, if you have the math background, it is something powerful. But of course, there should be a time for learning as well. Yes, we can do that, Özkan, for sure. I will be happy to answer the questions. So now, you know what? I wanted to put some visualizations from each of the project that I was mentioning. So this is the project that we worked for Manulife. It was about insurance data. And what do? You do comparisons, right? So you can do some visualizations. You can do some, provide some graphs. And these graphs were in R. This was not in Tableau, it was in R. And, we come up with some visualizations, right? And it's not only the visualization. When you say comparison, so let's say if you have really something interesting, like you're working on healthcare data and you have different age groups, right? And you want to see whether there is a significant difference between these two age groups, right? So when it comes to significance, of course, you can go to, again, test statistics, etc. But this part is a little bit for visualizations. So this is correlation analysis. Remember the cosine that I was mentioning between, two attributes? One line of code. This is just one line of code. Immediately you have the correlation, pairwise correlations for all the attributes that you have. And at first sight, you can see, oh, red one is negative correlation, blue is, positive correlation. If it is a little bit darker, stronger correlation, stronger negative or strong positive, right? So in diagonal, you see that, of course, year will be correlated with itself, like perfectly correlated, right? So that's why it's very thin and dark. So, one line of code. And then, of course, exploring the data. So when you say exploring the data, I take you to the multivariate level. So first of all, when you're doing initial analysis, univariate, correlation, bivariate. And then I want to take you to multivariate. Multivariate means that you're, connecting more than two attributes mainly. And there you go, data mining. So, and I was having a question about data mining. I think this is a good place to mention a little bit about that. So data mining is something that, so look at this scenario. So this table is from, again, Toronto Police Services collision data. And I'm sharing you a rule with you. By rule, I mean the following. If this attribute is having this level, if that attribute is having whatever level, then this attribute is having this level or this value. So it is really an if and then statement. And what it is doing is no predictions, just trying to extract some rules from the data set. Again, these are a few lines of codes in R or Python, doesn't matter. So here we use a priori algorithm. It is an association rule mining technique. And there are other association rule mining techniques as well that you can use, but this one was a priori algorithm. And again, a few lines of code, but you understand something in the data set, right? Especially if you put your dependent variable at the end, everything can come in terms of your dependent variable. So for example, that fatality that we had in the data set, we could see how inattentive drivers or impaired driving was causing, the fatality. So these are really about the stories about the data set. And you know what? When I say stories about the data set, or when people say stories about the data set, I have to mention, like, open-heartedly that it is technical. So those stories about the data set is coming from doing the analysis, doing the coding, understanding the output of the code, right? It's okay, one line of code, but it is giving you a full output and we have to understand it. So all those stories that is coming from the data set is really technical. And if we do the initial analysis, exploratory data analysis, and if we do those steps in detail, at the end, if we're doing predictions, the prediction results can be good as well, and we can learn something from the data. And then this part is about the predictions and validation. So you can see here that, I was mentioning you the training set and the test set, we are reporting our evaluations, and you can see it's not only one model that we are putting in our analysis. Of course, we need to compare some different algorithms, not only algorithms, but different experimental designs as well. So we put like randomly 80% to training and 20% to test set, or do we do it in a more systematic way? Can we do an experimental design in a way that in time the dependent variable is changing and we are doing our experimental design in a different fashion than traditional fashion? So these are also, good questions that we are asking. And of course, visualizations, tables, etc. are there. So this is about reproducible research. I know in math also, this is important, right? So when we get citations, we are happy, of course. So in data science, it's not only about the citation of the paper, but also it is the coding part. And I would suggest GitHub. Probably you have heard of GitHub, and it is really interesting that you can put your code, you can even collaborate on your code as well. And when you are producing a reproducible work, you mean that, okay, this is the research that I have done, this is the research paper that I have, and these are the codes, and you're giving the area for reproducibility. And this is interesting, especially some papers in neural networks is taking a lot of attention. And you know, Archive is the platform that it is open source, open access, and I'm sure that you know it from math as well. So you can put your paper there. I mean, before it is published, you can see that, especially if it is a hot topic in data science, people start to cite that work, because you know, I have examples of that, like hundreds of citations before publication, because there is a need there. So I can say that, you know, the different algorithms, different architectures in neural networks is a need, right? So we need, if it is faster, if it is less computationally complex, so there can be a need that you can see. And I will say a few things about the structure of the research paper or project. So this part may be a little bit different than the ones that you are using. So abstract, introduction, okay. So background and literature review is, you know, something that you can immediately think of. We have always a section that we are mentioning our data set and data description. That is mainly about the data, really. If it is not open source, you need to mention still some things, how the data was collected, you know, how the data was pre-processed. And if it is open source, we need to put the link. For example, Toronto Police was open source, so we put the link, the website, and where we get it from. Methodology is mainly about the methodology, right? It's about the methods that you have used in your paper. And then you go to results. So results section is interesting as well. It's not about only the prediction results, but also from your exploratory data analysis results. Remember the rules table that I was mentioning you? That is data mining. So it is not prediction, but you are getting something from exploratory data analysis by using data mining techniques, and you can get a result from that as well. And if your exploratory data analysis results somehow match with your prediction results or somehow support the prediction results, that is a happy end, I can say, right? Threats to validity is something that we put to our papers because, of course, we are working on an open source data set, and at the end of the day, it's a case study. And what are the threats to validity that we have seen, and what were the actions that we took to mitigate that problem? So let's say we had so many missing values, a scenario, we had so many missing values. Of course, we did some imputations, but how did we do the imputation? Did we take a little bit more sophisticated way to reduce that threat to validity? So, you know, internal, external, and also statistical. So there are different threats to validity that we mention in our papers. And then, of course, we go to conclusions, acknowledgements, especially when you have a collaborator, you know, that can be something that you need to discuss. So abstract is, you know, it is the same structure in math or any other major. It is the same. Importance of the abstract is important because that is how the papers are distributed somehow. And catching the attention in abstract is, I think, very important. And we mostly use structure abstract. So this structure abstract is something that I want to mention because IEEE is also using this, let's say, template for the abstract, and it became a common practice mentioning. So it's something like one paragraph abstract, but in the abstract, you really put everything that you have done. So if I read the abstract, I know what the result is, right? So not only the aim, not only the purpose, but also the results are there somehow in a short version. And that is a really good structure abstract, it is called. That is really a structure that we are using both for our project in the undergrad level, but also in the master's program. So this, when it is data science, as I mentioned, you're right. So in the very beginning, there is no happy end and it is iterative. So this means that if the accuracy results are low, maybe I can add some more attributes. Maybe I can go to a different algorithm. Maybe I can work on a different experimental design. So there are always different things to do, right? And that's why there is room for improvement. There is room for improvement. And if there is room for improvement, of course, we should report that in the conclusion. But however, please be careful that the work shouldn't be seen incomplete. So it should be something that you have done everything, you finalize your report, right, in terms of exploratory data analysis, prediction results, threats to validity, you evaluate your results. So all are done, but still there is room for improvement. If there is, go ahead and use it, work on it, and write it as next steps, let's say, or future work. This is something good, especially in data science, especially when you're working on data sets. So, and for future of data science, I want to share a few things with you. This is mainly, you all know that there is a growth in data science in terms of, growth in data in terms of really the data. And it is not only structured data, but it is social media data, right? So when you go to Twitter data, Facebook, or any other social media that you're using. So it is still huge. It was, even 5 years ago, when I was preparing the course materials, I was mentioning that in my course, mentioning that there is an exponential growth in data, and now it's even more, right? And cloud computing is again something that will be in the future for sure as well. So as you know, different companies are providing cloud platforms that you're not mainly downloading any program languages anymore, right? So you're running Python or R, but you don't have it in your computer, right? So you're running in the cloud, or even big data tools like Hadoop, Peak, Hive, or Spark. So cloud computing, I guess, still will be there, and it will have a good place. And deep learning is, by deep learning, of course, it is not only the rules that I was mentioning. For deep learning, it is interesting that by the help of deep learning, the algorithms are really learning, right? So, but it is not only the predictions that is coming into account. So, for example, by the idea of reinforcement learning, the algorithms are learning how to play, right? So, play some games or learn to play. So, for example, AlphaGo, if you want to read about that, so it was something that took a lot of attention, and that will be still there. So, I think deep learning will still be there. And when I say power of AI, I don't know, just think about driverless cars, right? So how it is changing, it will be changing our life. And so the thing is that the technique and the driverless cars, let's say, itself is there. And the thing about that is maybe about some regularizations and about law that is changing. And in terms of law, I can say that data ethics, privacy, and law and regularizations related to that will be very important as well. And when I say exponential growth in data, right, when I say social media data, just think about all of the things that is happening in Twitter and Facebook, and how data ethics is taking, part, and privacy, and also data regularizations will be, I think, very important in the very early future as well. So yeah, that is pretty much from my side. So thank you very much for attending this session. And if you have any questions, I will be more than happy to answer.
Well, let's first give her a virtual applause. How about that?
Thank you. Thank you for having me. Thank you for inviting me. Thank you very much.
That was a great talk. I'm literally saying that because we had in the past data scientists working in industry and giving us talks about data science, machine learning, and AI. And your talk is sort of like wrapping up everything. And also you are teaching these courses. So we never had a speaker, in fact, teaching data science before. They were just using data science in industry. So that's an awesome talk. So I'm going to leave the stage to people for questions. I think we can go over maybe 5 or 10 minutes. If you want to stay around, please stay around. If you need to go, you can go. But we're just ready to get questions for the speaker. You can simply unmute yourself.
I've got a few questions. I'll start with one. You mentioned testing and training sets, right? And I think there was like a 70-30 split or something between mostly training and then having some of the testing set. I think you mentioned briefly validation sets, and I've always been kind of maybe misunderstood what those are for. I thought they were for maybe tuning hyperparameters after a model is trained, but could you elaborate on that a little bit?
For sure, I will be happy to. So by hyperparameters, we mean, for example, since I mentioned k-nearest neighbors is using an entry k, let's say. So when I say k-nearest neighbors, I am the one to put that number. Is k going to be 5, 10, 6? Okay, so mostly it is 10. So when you go to some researches and when you read about it, okay, mostly it is 10. But why not 9, right? So in terms of this 10, 11, 10 is always the magical number somehow, right? When you do cross-validation, 10 cross-validation. So why not 9, right? So those kind of algorithms, so some of them are coming from the algorithm itself, right? So you're entering it to R or Python, so you're the one to choose K, right? So that is an hyperparameter, right? So choosing K, but you're using KNN, that is your algorithm for sure, but how about the best K? How can you optimize that K? And still you want to do some experiments, right? So in terms of K, there are some techniques that you can optimize K, but also you want to do some tests, let's say. So when you do that, you don't show that to the test set. So test set is something in your pocket. You will use it at the very end, right? So validation set is a set that you can tune your hyperparameters. And especially when you're using neural networks. So neural networks are using different activation functions, right? So to choose the best activation function, you can work on your validation set. So you will not show that part to your test set. Just think about that. I think this is the main basic way that I can mention. So you put your training set, you put your validation set, and then you put your test set in your pocket. And especially when you're doing feature selection, and at the end, when you're reducing features, I mean the attribute. So feature selection should be also done on the validation set. So because feature selections techniques, if you use it as an algorithm, is using the dependent variable as well. So just think that if I'm doing the feature selection by using the dependent variable, it's like cheating, right? So test set shouldn't see that. Test set is in my pocket, and I will not show the feature selection algorithm to the test set. So where am I going to go? I will go to the validation set. So that is the basic idea that can explain why we need a validation set. I hope I could answer your question, because I want to give the scenario behind, right? So why there is a need, kind of.
Yeah, very cool. Thank you.
Any other question for the speaker? Go Bruce, please.
Thank you for speaking today. I did enjoy the talk quite a bit. I had a question though. When I'm teaching it, like if I'm teaching somebody linear regression, simple single variable linear regression, I can take as little as 3 non-collinear points, and I can walk them through an example, and we can work it by hand. And I find that those examples help people better understand what's going on. I'm trying to wrap my head around machine learning, and in particular deep learning. But what's missing from that is the simple examples where they can say, okay, well, here's a simple example where you can kind of, what I get in most cases is, well, then you train your algorithm. Well, that's the part I want to understand. Don't just, that to me shouldn't be a sentence. That should be, so here is how we would train the algorithm, And I realize if you're doing it with thousands of things, you can't do it by hand, but there ought to be simple examples. So that's my question. are there simple examples out there that I just haven't found that explain that better?
Bruce, thank you so much for saying that. You know what? When I was learning, so learning is something that, I was giving time, reading textbooks and trying to understand how it is working. And especially when you go to the teaching part, just like you mentioned, right? So you can do linear regression, go to the fit line. So, this is the error. So residual. So just like think that, we are doing minimization. They're minimizing the error. Nobody wants error. So minimize the error. And when you're mentioning, let's say, why do you go to, let's say, squares and square roots? Why don't you go to absolute value? Well, it is a minimization problem. I will take the derivative. So everything is, even the theoretical part is crystal clear in our brain, right? And we can share it with our students. So, so this was a struggle that I had as well. So that's why in the courses that I was teaching, I prepared the video lectures on the content. So in the video lecture, there is no coding, let's say. So when I say k-nearest neighbors, I'm really putting this in. K-nearest neighbors is an advanced algorithm. Actually, it's a first of all nonlinear algorithm. It goes to distance measure, let's say Euclidean distance. It is nonlinear and computationally complex. Why? Because it goes to each and every row. It is taking the distances between attributes, using that measure, calculating, and then for each row it is running it again and again. And think that if you have more attributes, of course, more squares, and more calculation. So just let's think about this. K-nearest neighbors is doing the following. It is taking do you want 10, let's say, best 10 neighbors, okay? And doing going to the majority class if it is a classifier, going to the average of the distances if it is a regressor. So this very simple idea was not something that we were getting immediately from the let's say tutorials of the algorithm. So because we have to learn it first and then go to the tutorial of the algorithms, like packages mainly, to understand how it is working. And it is really taking time. In the courses that I'm teaching in the undergrad level and in the certificate program, so we are not wanting the students to write their own algorithm. They are using packages. And when they are using packages, I mean, thank you for mentioning that. I really feel the same thing. So when we are using packages, how is it working? What is the simple idea behind? Because believe me, all of them, including neural networks, have a simple idea behind. And in the master's level, for example, instead of using KNN package, students should write their own code. I think that is the place of real learning, but of course it is taking time, and not all courses can be designed in that way. But I think visualizations, understanding the algorithm, going through the packages, like in terms of tutorial understanding, is interesting. And one last thing, I mean, since you mentioned, I want to share one thing with you. We have taken topology courses, right, in the undergrad level, at least one course. So I was really impressed when I saw topological data analysis. So that is interesting. If you Google it or if you use a search engine, you will find 4 or 5 minutes of video in YouTube. Very interesting. Have a look. It is about the shape of the data and how they are using topology and kernels to show the shape of the data. The generic examples that we have about a coffee mug and a bagel, let's say, right? So those ideas. So it is just 4 or 5 minutes. Just have a look. I think you will like it. I never taught that part. I gave a seminar. I was very interested. But yeah, I mean, math is there, and when we understand more, I think it will be more interesting for all of us.
Well, and it's frustrating to me. I'm taking a class in data analytics actually, and but it's in the business college. And I mean, using something like RapidMiner, for example, these things exist, but they're absolute black boxes. And everyone seems fairly content. It's like, oh yeah, just put it in the deep learning, see what comes out. I'm like, I just can't hardly operate like that.
But it will be they call it black box, right? So put it and then get something. So, I mean, I don't want to say something negative about that at this point, but I really don't feel comfortable. Maybe it is my thing. It is when I do not have control, it is not that comfortable. And you know what, even neural networks. So for example, very simple idea. You mentioned linear regression. Linear regression, going to logistic regression is really one step away. When you go to neural networks, instead of that log function, you can change the activation function as well. So actually, the people who have done these algorithms or who have worked on this were using the simple ideas, and they were really structuring or constructing one thing on top of the other. The neural networks or deep learning was not coming in a second, right? So they were really improving their model, so one step at a time. And if you check those architectures in neural networks, so there is a huge math behind, and I think it is well structured.
Thanks.
All right, we have a question, I think. Thanks, by the way, for the answer. Yeah, we have a question from Megan, I think, right?
Hi, yeah. So my question is more in regards to sharing code. So you mentioned, data sets that are open source versus data that is, from a private company, and how important it is to, share code for reproducible research. And also for new data scientists, it's important that we're able to show what we're able to do, to potential employers or other collaborators. So my question is, if you're working with a private data set, so for example, sometimes I do a little bit of clinical data analysis. Is it okay to post your code? No. Okay.
So
you
NDAs, yeah. So for example, Toronto police data, so I got your point, Megan. Yeah, very, very good point. So in Toronto police data, it was open source. And even if you go to their website, there is a Vision Zero project that the Toronto police is, trying to reduce the number of collisions to zero. So in the website also you see some visualizations. The data set is there, but this is interesting. This is open to public, right? But when you go to healthcare data, insurance data, not codes, nothing. Even when we are writing the paper, the numbers in the paper in initial analysis or exploratory data analysis, just the numbers about the data, right? Let's say some kind of percentages you will put, right? Those are approximated. And we mention it in the paper that those are not exact numbers. And it is fully anonymized and encrypted data, so nothing is understood, but still, even while we are writing the papers, we had some restrictions, code, etc. We cannot. I mean, it depends, of course, to your NDA, but in my case, we couldn't. So very good point. I mean, since this was, when I was mentioning the research project and when I was mentioning the paper part, it's mostly for our students. So if a student, that's why, in Ryerson or any other university, as far as I understand, so they cannot work on private data. University cannot work on a private data. So those projects that I was mentioning was really at the collaboration level with data science lab, that data science lab was getting the project and we were working for the project. But in terms of students, instructors, supervisors, we cannot work on private data. Even in the master's level, the data should be open source because it is for educational purposes.
Thank you.
My pleasure. Thank you.
Thank you. Any other question?
I've got a question about activation functions. So I know that there's some simple ones like the sigmoid function or maybe like the ReLU function, stuff like that. I'm wondering if those are treated as hyperparameters, and if they are, if there's like some set that you muck around with to see like which ones fit what you're trying to do, or if there's like an intuition behind which activation functions you pick.
So actually you can use again some experiments. So that intuition, especially at that level, like when you have big data, so many rows, so that intuition about the activation functions is hard to catch because there are so small minor differences between one another. So what we do is really work on a validation set and do experiments there. So, you know, some intuition can come. For example, when you think that the data has a nonlinearity in it, so instead of going to a linear algorithm, you can go to nonlinear algorithm, you know? So that kind of intuition can come a little bit, but in terms of the activation functions, which one to choose, we go to experiments, I would say.
Okay, thank you.
I mean, it would be good to have that, but, you know, so I'm not in that level, at least.
There's a question, where would you be willing to share your slides?
Yeah, that's what I was going to ask.
Sure. So I already shared it with Özkan. So for sure, Özkan. So however you want.
Yeah, I'll do that.
Yeah, for sure.
Any other questions for the speaker?
I have one more
I
question.
do have one question if there's nobody else. Yeah, go for it, DJ.
So I just
Go for it.
wondered, is the research developing different machine learning or deep learning models, or is it more like applying models and interpreting the results?
Oh, okay. So when I was mentioning like open source or, you know, the data sets that I was working on, you know, all the projects that I mentioned here was implementation. So I didn't write my own algorithm. So in terms of, I mean, I didn't come up with a new algorithm. I used, I mean, and my team used existing algorithms and, you know, produce results. So there is nothing sophisticated, right? So we are using the simple algorithms in a sophisticated way, I can say. But there is nothing that, but actually that level would be something really good. So coming with, but at that point, you know, writing a paper for a new algorithm, like newly developed, you developed an algorithm, you came up with your own algorithm, and writing a paper for that would be different. So because your test shouldn't be on one data set at that point. You have to go to different data sets, do some analysis, do some testing there. So these are really on one data set. And we are sometimes taking some external attributes as well to the system. For example, in the insurance data, we did that. So, but still, we are using the existing algorithms and existing analysis. But there are different approaches. I mean, even if you use the same algorithm, of course, the approach that you're taking with feature selection, experimental design, and then the algorithms, each one is a unique study, I would say. But that is the scenario. I had a question. Sorry.
I was just going to say to DJ real quick that I have met some people that actually have done a little research in functional analysis of data science. So there is some PhD level math research that's being done in data science too.
Exactly. Even
I have one quick question, and I think go ahead. Yeah. Jenny, sorry. Go ahead. Yeah.
Mentioning topological data analysis, I would say.
Yeah, that's right.
Yeah, exactly. So all of those are, yeah, for sure.
Thank you.
All right, one tough question. So I may have like a biased network in my LinkedIn and in my connections. So all of the people that I know who worked partial differential equations in the past, one way or another, somehow now having a career in data science, and you are not the first person that I saw, like, you know, working on PD models and stuff. Then all of a sudden you're like, data science is awesome, you know. And even past speakers had the same kind of like background. So am I wrong on this, that, you know, like if you have like a good PD function analysis background, that you could turn those skills into data science easily, or is that a wrong statement?
No, this is a correct statement, Özkan. I think so. And also, again, the things that I shared with you today, believe me, it's not in the PhD level. So, you know, in terms of the math behind. So in terms of the algorithms, of course, I mean, there are PhD students who work in these teams for sure. And some of the projects can be a PhD thesis even. I don't mean that, but in terms of the level of math. So, but if we use the level of math, like as you mentioned, like functional analysis or topology or something else, we can really use and come up with new algorithms. So I think that will be really something really cool. But in the papers that I mentioned, I wouldn't say that I took it to that level. So and in terms of, I think, partial differential equations that you mentioned, like the changing the major, I think it is about applying math. So I was always mentioning that I work in applied math, but when I started to work in data science, I really saw that I'm really applying math, kind of. So
Jenny, you know what? You were my TA when I was an undergraduate student. You were my TA when I was an undergraduate student, and then you were my inspiration that you were working in the field of partial differential equations. And that was not the main reason, but one of the reasons why I got into grad school and started working on PD models that time. So that's why I'm intentionally asking this question to you. And then apparently there is some kind of like skill set transfer from. What's that?
You were our best students. Don't change the topic. So when I was TA.
Oh, thank you. But that was seriously, I mean, like, I have some other people in the list that I plan to invite for future SIAM talks, and they have they're somehow related to partial differential equations, control theory, one way or another. So, but you answered that question. I think that most of the skills are transferred all the way to data science and rewriting new algorithms and stuff. So that's awesome. So at that moment, I want to take a word from you that maybe in the future I may invite you again, because this was one of the best talks that about like data science and everything. So would you just give us another talk maybe next year, maybe next spring, or you probably have more stuff to show us. And if you have anything to advertise, by the way, about your program, go ahead and do it right now.
For sure. I mean, for sure, I will be happy to join again. Why not? For sure. So it was a very.
Do you have any kind of like stuff to share about your program?
At this point now.
Okay. Okay.
Oh, sure.
Just wanted to double check.
I couldn't get the question. So do you want
the program that you said, the master's program and the undergraduate program at Ryerson? Do you have anything to share with our speakers? If so, please share with me. I'll just direct them all the way to their way.
Sure. I mean, I think in my talk I put some in the flyer. We put the links as well to the program. So we have two programs of data science mainly. So those are for adult learners, but also engineering and math students are taking those courses as elective courses. All of the courses that I was mentioning to you in the program, not only the ones that I'm teaching, but the other courses as well, or our degree credit courses. So that's why our students are taking those courses as elective courses for their program. But also we have adult learners who are coming from industry or who are not, who want to change their major, for example. And these courses are, can take you to different levels, I would say. So mostly they ask me, can one become a data scientist in 6 courses? Well, my answer is yes, because these courses are major courses. So for example, I'm from engineering of mathematics, right? So, and I don't know how many courses we are taking in undergrad, 40 courses, 50 courses. Are we using all of those? Of course, we are using 5, 6, 7 of them as major. So depending on the background that you have, okay, maybe computer science, maybe, business or IT or math or physics even, those courses can take you to a place in data science if you like. So I think the background that you have, I don't say that only 6 courses are enough, but there is a background. So with those 6 courses, you can build a background and you can understand better. So the first program is the first program, and it has 5 courses and the project course. And the second program has 3 courses and the project course again. But the second program, the practical machine learning program, is the advanced one. So we have to finalize the first one and then pass to the other. But if you have the credentials, if you get the department consent, you can go to the advanced program as well. And master's is taking really a lot of attention. So master's degree program, because it is it is all the courses that we are teaching in Ryerson and in Cheng School are all evening courses. So master program is evening courses as well. So you can do the master's in 2 years or in 1 year, depending on being a full-time student or part-time student. And yeah, all of those courses are either evening courses or Saturday courses. You can choose Saturday courses as well. And the certificate programs are all, each course is having 4 or 5 sessions. So students are finding an appropriate time for themselves. And we have students who have full-time jobs and taking, let's say, 1 or 2 courses per semester. So this is pretty much our life in data science in Ryerson.
All right, let's give a big virtual applause to her.
Thank you
Well,
for coming.
let's-
Thank you
yeah.
for attending. I had a very nice Friday afternoon here in Toronto, so I think it's because.
What else could we do for a Friday night, right?
Sorry, may I
What
ask a
else
question?
could we do? Go ahead, yeah. I think we're overtime. Yeah, go ahead.
Sorry, thank you very much for the information. I need to know what are the prerequisites for starting the first certificate program, data analytics at Ryerson? And is it more regarding math or more regarding statistics? I need to know about the prerequisites actually.
The first, yeah, very good question. The first certificate does not have a prerequisite like because we are building, you know, from the beginning, so it doesn't have a prerequisite. So I would say I need to double check, but some math is needed, but it is I don't know which level it is. I need to double check, but there is no prerequisite for that one. The second certificate has a lot of prerequisites, and of course, master's admission is a little challenging, and there is a big competition going on there. You can imagine that in terms of the number of students who are applying. But for the first certificate, for example, the course that I was mentioning, CIND 123 basic methods, data analytics basic methods, we are starting with, you know, standard deviation or normal distribution or Poisson distribution, some discrete distributions, linear regression. We are giving the statistics background together with a programming language. We are using R there, and then we pass to Python. So that's why, I mean, pretty much it is not a statistic course, I may say, but we are taking the basics that will be needed in data science, and we are teaching that. So that's why it's like building really a structure. So 3 courses are the first courses that you're taking, and then there are 2 courses which are advanced. So the previous 3 courses are the prerequisite, and then you do the project course. And for the other certificate, which has 3 courses plus a project course, each course is a prerequisite of one another. We want the students to take that one course at a time, because we need to learn and digest, and it takes some time, especially when you go to a little bit to the advanced level.
Okay, thank you so much.
My pleasure.
Thank you. I think let's end the session and let's give some time. Jenny, she's already exhausted, I think. She's been speaking for like, what, 90 minutes? Yeah.
I'm okay with that.
All right. Thank you so much, Jenny. Thanks for coming. Thanks all for coming. And buckle up for the next event. I already mentioned to you that's in April. That's on April 23rd. We're inviting someone from UMBC. I'll make separate announcements for that. All right. Thanks again. And then see you guys later.
Take
Thank
care.
you.